Hi, everybody. Welcome to Chapter 15, Power. We are talking about the Power chapter. Now, this chapter is a little bit different than the other ones we've talked about. So we're going to start with this first part. So the first part of this chapter is going to be just about what the concept of power means. And the second part is going to be doing some calculations of how to get to power. So the first thing we need to do is review a little bit. We need to review some basic concepts about hypothesis testing. So go ahead and answer this question. Okay, the probability of making a type 1 error is what you choose it to be. That is alpha. Alpha is the probability of making a type 1 error. Beta is the probability of making type 2 error. 1 minus alpha is the probability of being correct if the null hypothesis is actually true in reality. And 1 minus beta, that's power. Now, what am I talking about? Let's go ahead and take a look at this. Do you remember these concepts? This is the type 1 and type 2 error chart that we've looked at before. This is your decision. You're either going to reject the null or fail to reject the null hypothesis. But in reality, the null is either true or it is false. Now remember, we don't know what reality actually is going on. We don't know. We don't know if the null is true or if the null is false. And so far, when we've been discussing things in our in hypothesis testing, we've been talking about what if the null is true. Remember, we talked about the p-value, which is the probability of getting the statistic if the null hypothesis is true. We're looking at the sampling distribution when we're looking at whether the null is true. That is all the values of a statistic and the probability of getting them if the null hypothesis is true. But in reality, we don't want to be here, okay? We want to be here. In fact, specifically, we want to be right there. This box is the one that we want. When we're talking about power, we're talking about the power of your experiment or your study to get what you want. So let's do an example to make sure that we're all clear. Let's say that I've invented a love potion. And I don't know if it works or not. I think it does, but I'm not sure. So I'm running my experiment to see if I can say that my love potion actually works. All right, well, if the null hypothesis is true, then that means my love potion does not work, okay? The null is that my love potion doesn't work. Null. Nothing's going on. It doesn't work. Okay? But if the null is false over here, that means my love potion works. If my love potion works, I'm going to run a study. And in my study, I'm either going to be correct in rejecting the null. Okay, my decision would be, hey, my love potion works, and I'm going to go tell the world that it works. If it does work, then I'm here. And that's where I want it to be. I think my love potion works. I want it to work. And so I hope my study can find that it actually does work. Failing to reject the null hypothesis would mean, boy, after I did my study, my conclusion was it didn't work. Now, if my love potion actually works and I go out and say it doesn't work, then I would be making a type 2 error. I want to be here. I want to be here. So far in hypothesis testing, we've been all about here, okay? All about right there. And now we're going to be talking about power, which is right here. We're going to use that example of the love potion for our example, okay? And remember, the power is the power of the study, the power of my experiment to find that the null is false when it actually is false, for us to be able to go out and say, hey, the love potion works when it actually does work. All right, let's say I'm going to give you a scenario of the study that I've got. So let's say I've got this love potion and I want to see if it works or not. And I've got 8 people who are willing to try this love potion. And what I'm going to do is I'm going to figure out whether or not they fall in love after a month. So let's take a look at some things. The power would be the power of my specific experiment. So the power of my experiment with 8 people to find that the love potion works when it actually does. So power is actually the probability of the experiment resulting in rejection of the null hypothesis when the null is actually false. So the other way to say it is the probability of me finding that my love potion works when it actually works. So it's all, the other way to think about it is finding the result, that is rejecting the null hypothesis, when the independent variable really does have the effect on the dependent variable. All right, so for our example, the independent variable is the love potion, and the real effect would be whether or not people fall in love. The dependent variable would be whether or not people actually fall in love. So let's make this particular experiment about, let's make it a binomial. So um, in this case, the binomial would be whether or not somebody falls in love after a month. Now, this is going to depend on several things. The power of my experiment is going to depend on several things. The first is how big of an N I have. Now, remember, I'm going to have 8 people in our example. If I had more people, I would have more power to find the effect, to see if my love potion actually worked. The other thing is the size of the real effect, what's also called the effect size. That is, how much of an influence does my love potion have on falling in love? Does it, make you like 1% more likely to fall in love, or like 50% more likely to fall in love? That is the size of the effect. 1% would be a small effect size, and 50% would be super big. The other is controlling for other variables, right? So for example, if I was doing a love experiment, I would need to say, oh, well, you know, people can't people can't buy new outfits or other things that might affect whether or not they fall in love with somebody else, right? So in statistics, we're going to worry more about N, how many people we have in the study, and the size of the real effect, called the effect size. Now we're going to be talking about power. We already knew that it's power equals 1 minus, beta equals 1 minus power, right? And we need this. This is what I was looking for, the binomial power. So when we're looking at what's going on with a study, so remember my study is I'm going to have 8 people, only 8. There's only 8 people in my study. That's all I could get to sign up. And they're each going to take my love potion every day for a month. So I've got 8 single people, and they're each going to take the love potion one day, every day for a month. Now, if the null hypothesis is true, that means my love potion doesn't work. But even if my love potion doesn't work, I could still have people falling in love. So let's say that, if everything is normal, about 50% would fall in love. So the probability of the null is the probability of getting a result. In this case, people fell in love when the IV has no effect, when the love potion has no effect. In this case, that's about a 50% chance, right? So it's half and half. About half the people are going to fall in love, about half aren't. The P sub real, that's the probability of getting the result when the love potion actually works. Now, it's not going to be 50%, because 50% is what's happening when nothing's going on, right? When nothing's going on, I'd expect about a 50-50 of people falling in love. So we get to decide what the effect size is. Well, we don't just decide it. We make a good guess. Since we don't know how effective the love potion actually is or isn't, we have to guess on it or use prior knowledge, etc. And so let's go ahead and say this. Well, I think that the probability of, if nothing's going on, about 50% of the population is going to fall in love. But with my love potion, I don't think it's 100%, right? I don't think that it's going to cause everybody to fall in love, because, there's some people who just aren't going to fall in love, even with my powerful love potion. So let's say that with the love potion, if the love potion is working, I think that 80% of the people who take my love potion are actually going to fall in love. That would be the probability of the real, P sub real. In this case, would be 80%. The effect of the love potion would be that 80% fall in love. If the love potion doesn't work, I would still expect about 50% of the people to fall in love. So what does this mean? We're talking about a binomial now. So the outcome is you either fall in love or you don't. Those are the 2 outcomes, okay? All right, now if nothing's happening, if my love potion doesn't work, 50% are going to fall in love. If my love potion does work, I predict that 80% are going to fall in love. So what I'm going to show you right now is let's find it. Let's find the binomial. Where are you, binomial? That's not you. All right, the binomial, that is my kids' kindergarten class. That is not the binomial. Come back, binomial. Here we go. This is the binomial table, the one that we've worked on in the past. All right. Remember, we think that if the love potion doesn't work, 50%, 0.5 right here, 50% of the people are going to fall in love. If we think that it does work, then we think 80% of the people are going to fall in love. Well, this is n sub 8. That means we've got 8 people here, and the possible outcomes are 0 people could fall in love, 1 person could fall in love, 2, 3, 4, 5, 6, 7, 8, etc. Then, if the null hypothesis is true, then these are the ones that we care about right here. Okay? If the null hypothesis is true, if my love potion doesn't work, then the probability of 0 people falling in love is 0.0039, etc. Over here, these would be the probabilities if my love potion does work. Remember, I think that the probability would be 80%. And so these would be the probabilities if the love potion does work. I've copied these over and I put them into this table right here. So this is the same information. If my love potion doesn't work, then I'd expect 50% of the people to fall in love. Okay? And these are the probabilities of each number of people out of 8 falling in love if it doesn't work, right? And this is what we've been working with so far when we're talking about p-values and rejecting and failing to reject the null hypothesis. We've said, hey, well, I'll accept 50%, excuse me, a 5%, 0.05, and alpha equals 0.05. That means I'll accept a 5% chance of rejecting the null when the null is true. Well, when the null is true, that's this column right here. And I'll only accept a 50% chance. Now let's go ahead and do a one-tailed test to make this easy for ourselves. That means I only think that my love potion can make you more in love. I don't think it can make you less in love. Whether I should do that or is a separate question, but let's make it a one-tailed test right now. So what we're saying is, I think that we're going to be on this end of the spectrum. Now I'm going to show you on this particular chart what we're talking about. So we start with 8, right? We start with the probability of 8 people falling in love. 8 people falling in love. The probability of that happening when the null is true is 0.0039. So I'm going to go over here. You see it right here, 0.0039. That is this one right there. That is less than 0.05. So if 8 out of 8 people fall in love, well, the probability of that happening when the love potion doesn't work is super small. It's 0.0039. So we'd still reject the null hypothesis. Well, what about if 7 people fall in love? If 7 people fall in love, then we know that the value 0.0312, that's the probability of 7 out of 8 people falling in love when the love potion doesn't work. So 0.03125 plus 0.0039, that's still less than 0.05. And so if 7 or 8 people fall in love, then we're going to reject the null hypothesis. This is review. This is stuff we've already done. Now we look here at number 6. If 6 people fall in love, then the probability of that happening when the love potion doesn't work is 10%. In fact, it's a little over 10%. Well, our alpha, the limit that we're willing to accept, is 5%. So already we know that we can't accept 6. If 6 out of 8 people fall in love, then it's not enough. We'll have to fail to reject. So only 7 or 8 people can fall in love for us to reject the null hypothesis. All right. That's all stuff we've done before. Now what we're going to do is we're going to look at this other group, because if 7 or 8 people fall in love, we know we're going to reject the null hypothesis. But could it be that if it works, that we wouldn't get 7 or 8 people? So let me show you what I mean. I'm going to show you the graph of the other distribution. This is if my love potion works. The probability of, let's say, 5 people falling in love, if my love potion does work, is 14%. But the problem is, we've already determined in that other distribution, we've already determined that we are not going to reject the null hypothesis unless we get 7 or 8 people. Is it possible that 0, 1, 2, 3, 4, 5, or 6 people could fall in love even if it does work? Well, the answer is yes, obviously, because 80%, these are the probabilities. 0, 1, 2, 3, 4, 5, and 6 people, all of those, those could happen if my love potion actually does work. But we've already determined that we're going to fail to reject that happens. In fact, we are only going to reject the null hypothesis if 7 or 8 people actually fall in love after that happens. Well, here's what happens with this. What is the probability of 7 or 8 people falling in love when it works? This is power. The probability of getting the result, in this case, rejecting the null hypothesis, when the null is actually false. It is us saying, being able to say the love potion works when it actually works. Well, we've already determined that we can only reject the null hypothesis if 7 or 8 people fall in love. If the love potion works, the probability of 7 people falling in love is about 33.5%, 0.3355. If 8 people fall in love, the probability of that happening is 0.1678. It's these probabilities right here, 1 and 7 and 8. Okay? When we add those two probabilities together, that's going to be our power. The reason why we're only doing 7 and 8 is because when we're looking at rejecting the null hypothesis, only 7 or 8, the probability of those happening is less than 0.05. So that means we can only look at 7 and 8 over here, if it really does work, to see what is the probability of us actually finding the result. And the sum of that is really close to 50%. Yeah, exactly 0.5033. We only have a 50% chance. This is power right here. The probability of us being able to say that the love potion works when it actually works. If it really works, we still only have a 50% chance of that happening. That's based on the number of people we have, 8 in the study, and also how big of an effect my love potion is actually going to have. Remember, I think that about 80% are going to fall in love. If my love potion had a bigger effect, like 90 or 100% of the people fell in love, then this would change. The power would change. If I had more people in the study, the power would also change. It would increase. But in this particular case, that's not what we have. We have 8 people, and we think that 80% are going to fall in love. And if that's the case, then even if everything works out the way I plan, I only have a 50% chance of my study coming to the conclusion that I want it to. That's what power is about. So here's what I want you to do. I want you to calculate power for a different study. Let's say that instead of having 8 people in my study, let's say that I have 10 people in my study. So we'll keep everything the same except for the everything the same except for the number of people. So now I've got 10 people in my study. So we're still looking at a one-tailed test, alpha equals 0.05. We still think that the null hypothesis, 50% of the people have a chance of falling in love without my love potion. We still think that 80% are going to fall in love with my love potion. So what we're going to do now is we are going to see what changes if we do 10 people. In fact, you know what I'm going to do? I'm going to change my mind. So now I want you to do the same thing, except we're going to look at 12 people. I'm going to look at 12 people. So we'll keep everything the same, except that I want to look at the study if I had 12 people. So that means I still think that 50% of the time, if my love potion doesn't work, people are going to fall in love by themselves with the love potion not working. That's the null hypothesis being true. And if my love potion does work, I think it's 80% of the time that it's going to work. Okay? If that is the case, then what would be the probability of me being able to reject the null when the null is actually false with alpha equals 0.05 in a one-tailed test? All right, so let's go ahead and test that out. So to calculate power, what we're doing right here is we're saying, well, first of all, if this is a one-tailed test, then I got to start at the tail, and my alpha is still 0.05, so I've got to add up the tail, just like we've done in the past. So I'm starting with 12 out of 12 people falling in love. The probability of that happening is 0.000244. If 11 people fall in love, that's 0.00293. So 0.00244, that's less than 0.05. If I add 0.00293, that's still less than 0.05. If I add 10 out of 12 people, 0.16 plus 0.0293 plus 0.0224, all that together is still less than 0.05. And just to make sure that you can see that it's less than 0.05, let me show you on a calculator what we're discussing. So let's make it show the calculator here on, make a calculator smaller. All we're doing is adding up those probabilities. So we're looking at 0.0000244. That's the probability of 12 out of 12, less 0.00293 plus 0.016113. And when we do all of those, we get 0.019287. So the probability of 10, 11, or 12 people falling in love when the love potion doesn't work is 0.019287. This is the p-value, by the way. The p-value of 10 or more people is 0.019287. If I added 9 out of 10 people falling in love, I'd go over 0.05. So I know that I can only have 10, 11, or 12 people fall in love when the love potion doesn't work for me to reject the null hypothesis. Now, I think that my love potion actually does work. That's here, 0.8. And so remember, I can only do 10, 11, and 12 because those are the only ones that fit in rejecting the null hypothesis. So now what I'm going to do is I am going to start all over again and do the same thing. I'm going to add up the probabilities in the 0.8 column for 12 people falling in love, 11 people falling in love, and 10 people falling in love. So I'm going to add right here 0.068719, 0.068719 plus 0.20615. That's how many, that's the probability if 11 people fall in love, if it works, plus 0.283468. So this 0.5583 is power. That's the probability of me being able to reject the null hypothesis when it is actually false. It is the probability if I have 10 people with a one-tailed test, alpha equals 0.05, and the effect is 80%, that is the 80% of the people would fall in love. If that is the case, then my test with 10 people has a 55%, 55.83, so close to a 56% chance of actually working. So the power is 0.558345. That is the probability of me being able to say my love potion works when it actually does. It's only a 56% chance of happening. There's another way to look at power. And let's talk about, instead of the binomial, let's look at what a curve looks like, because power is not just for the binomial, it's for t-tests and z-tests and everything else. So what we're going to do is we're going to go away from the binomial now, and we're going to look at curves. So let's say that this is the z-table. Now, here at the bottom axis, this is not z-scores. Those are what's called Cohen's d, and we'll get to that in just a little bit. But this is the curve of the probability of the null hypothesis, right? So this is the sampling distribution. It's the probability of any value of a statistic when the null hypothesis is true. So let's say that we were doing our same study, but instead of saying whether or not you actually fell in love or not, that would be a binomial. Let's say that we measured your love score, and your love score was measured on a scale from 0 to 10. All right? And so let's say that right here, this would be the average love that we would expect after a month if the love potion doesn't work. All right? So let's say that the average love, if the love potion doesn't work, would be, I don't know, something like 2. So the z-score would be 0, but it would be 2. All right? For us to be able to reject the null hypothesis, then we would have to have a z-score of at least 1.96. This is a two-tailed test, right? 1.96 or greater, or negative 1.96 or more extreme, right? in order for us to reject the null hypothesis. Remember, this is the null. In reality, though, there's a separate curve. We've been playing with this curve this whole semester. It's the same curve we've talked about when the null is true. It's a sampling distribution. But in reality, there's another curve. This was the null curve that we've been messing with. This would be if my love potion actually worked. If my hypothesis actually worked, there would be another curve. So what this is saying is that, you know what, I think that if my love potion actually works, the z-score would be somewhere around, and I'm not sure what this would actually be. Let's say let's say that the z-score is 2.5. The average z-score, if it works, would be 2.5. Well, that doesn't mean that we couldn't have more z-scores, z-scores that are higher, or z-scores that are lower, right? So what would happen if my love potion actually works? Let's say my love potion actually does work. Is it possible that I could get a z-score of -2? Well, it's possible. That's possible. All right, what you see right here is that demonstration. Everything on this side of the critical value, right? All of this is power, the probability of me being able to say that the love potion works when it actually does, to be able to reject the null when it's actually true. The reason why this is the power is because it's on this side of the critical value, okay? However, there's part of my portion, even if the love potion worked, that I'd still have to reject the null, right? What if I got a z-score of, -2? Well, if that's the case, then I would be making a type 2 error. So what you're looking at when we're looking at power is everything that's beyond the critical value, not in the distribution for the null hypothesis, in the distribution for the hypothesis if it actually works, right? All of this. So if I got any of these scores, if I got a z-score of 2.5, which would be our mean, plus, or 3 or 4 or 4, all of those things, if I got those, then I'd have the power to say the love potion works when it actually does work. However, if I get less than 1.96, then the love potion still works in real life, but I have to fail to reject the null. I have to say that it doesn't work. I'm making a type 2 error. Alpha is on the null hypothesis curve. Beta is on when your alternative hypothesis curve, right? Power is 1 minus beta. It's all the rest of the curve when the null hypothesis is not true. That is, when the alternative hypothesis is true. 1 minus alpha is all of this other stuff over here, right? All that, okay? All this stuff in the middle. We want our scores to be in here. We do not want to make a type 1 or a type 2 error. We want to have power. And this power changes based off of several things. So what if, if the love potion works, but it doesn't, it doesn't work very well, well, then this is what power would look like. And notice that the rest is going to be your beta, right? It's you going out there and saying the love potion doesn't work when it actually does work. This would be your power of you saying that it works when it does work. So it depends on how big the effect size is. You can just spread this out. And you'll see the lower the effect size, the less power. The bigger the effect size, the more power. Other things that affect it include your sample size. So let's see what happens when I change the sample size as well. Let's go ahead and put this effect size right at 1. Okay, that's a 1 effect size. See what happens when we add more people. The curves change, right? This would be if I have 52 people in my sample compared to 20 is what we were looking at before. However, if I only have, how many is this? 13 people in my sample, this is what it looks like, right? The more people, the more power, okay? The bigger the effect size, the more power. All of those things change the amount of power that we have. And power is our ability, say, to reject the null hypothesis when the null is actually false. It's our ability to say the love potion works when it actually does. All right. Let's go ahead and stop here and we'll do some more calculations in the next video.